Welcome to this special episode of Frequency Matters, the RF and Microwave Update series. I'm Pat Hindle, and today I'm talking with GP, Senior Director of Aerospace and Defense Strategy at Infineon Hi-Rel. Welcome, GP.
Thank you, Pat. Good to talk to you.
So your group supplies rad-hard and rad-tolerant ICs and discretes. So I thought it'd be a great idea to kind of dig into some of the specifics of your gallium nitride power devices. So, what are the primary advantages of gallium nitride devices over traditional silicon-based components in space applications?
Fundamentally, it comes down to power density and speed. GaN has higher electron mobility than silicon, and GaN can switch 100x faster in silicon with lower switching losses. This allows us to shrink the entire power system, not just the chip, but also the passives around it. So making electronics smaller and lighter. Incidentally, at home, we would have seen these power adapters that we have. We used to have a bigger brick. Nowadays, it's actually much smaller. That's because of GaN, and the associated passives are much smaller. And exactly size and weight are the key care abouts for space applications as well, making it an ideal candidate.
And how does the inherent radiation hardness of GaN devices enable the adoption of space environments?
So GaN is structurally superior for space fundamentally because it actually lacks a gate oxide layer. In general, when we expose a semiconductor to space, the radiation traps charges in that oxide. So we don't have an oxide, so that puts a significant advantage. There is no charge trapping, leading to the fact that it can actually survive in a LEO or a MEO or a GEO for a longer duration that is required for a rad hard component that gets used. Only thing that we need to worry about is actually single event effects, the heavy ion that actually goes into a semiconductor. GaN tends to perform really well in those aspects as well. In fact, for low orbit satellites, where it's actually the products that we propose are radiation tolerant devices, which the effect post SEE is actually a leakage that leads to small efficiency loss. We do have also for geo use cases radiation hardened GaN, where at IR Hi-Rel, we have a long history of robust, high reliability products that we do for space market. We run the same test and qualifications to withstand the high radiation environments. And for a geo orbit, for GaN, our designers actually change the structure itself to withstand more magnetic field, making it ideal candidate for space use cases.
Well, you talked about shrinking the footprint. What challenges are associated with the thermal management of GaN components in spacecraft systems?
That's a great question, Pat. As we all know, satellites are becoming very powerful these days. More processing in satellite means the power management that is associated is actually much more stringent. Now, with GaN, being able to do it smaller with an extreme power density, what that means is we actually have it to be smaller, as you rightly put, that leads to some thermal challenges. And what it creates is micro hotspots, the massive amount of heat in a very small, tiny package. And space engineers are adopting commercially available packages with multiple cool options to be able to work around those. Plastic packages that has ability to have multiple cooling that is commercially being used is also being adopted in space.
And in what ways has the rapid adoption of GaN technology influenced the design and performance of satellite power systems?
So it has enabled us to move to high frequency switching as well as decentralized power. GaN allows us to really have tiny, highly efficient converters from a point of use cases. So I'll take a simple satellite block diagram and talk through different use cases. To the right, where we have digital satellite payload, which is where we power the FPGA, one of the most power hungry elements in a satellite. And for example, a Versal 1902 actually takes 40 amps per phase, and they have four phases, which is 160 amps at zero point 0.7, zero point 0.6 volts. That's a lot of power. And there you can see medium voltage 40 volt GaN transistors replacing the MOSFET. The controller and the driver chip actually drives GaN. You get efficiencies that are much, much better, smaller size, faster switching, much more efficient when it comes to the point of load use cases. And then other places where we see in the satellites are actually in motor drivers, which are the reaction wheels, ion thrusters, and intermediate bus converters, which is the 28 volt bus, gets converted down to the voltage. There you see 100 volt medium voltage GaN transistors, which we have released. As we go further to the left at the bus voltage, where the traditional power need from a satellite being higher these days, companies are moving from a 28 volt bus to a 100 volt or 120 volt bus. There, customers tend to use a 200 volt GaN or sometimes even higher. High voltage GaN, moving from a medium voltage to a high voltage GaN up to 650 volts, which can actually handle transients north of 400 volts while withstanding the single event effects and can support all the use cases. This reduces the line losses, allows satellite to handle high bandwidth tasks like 5G, direct to cell, radar imaging, which are much more power intense and a lot more processing that gets enabled with GaN being used at multiple places in the satellite.
And how does the use of GaN technology affect the overall cost, weight, and efficiency of spaceborne electronic systems?
It's actually, I will say, it's a triple win. The first being efficiency. With a GaN based system, you can get north of 95% efficiency, which leads to smaller solar cells for the same use case that you are targeting from a traditional methods. Ability, the second one is ability of the GaN to switch much faster leads to smaller size of the overall power system, not just the chip, but also the passives around it. And going from a hermetic package into a plastic package also helps to shrink sizes. Now, when you have everything smaller, you have the weight associated with the satellite and the power electronics is smaller, launch costs are smaller, so everything is great. And the third one, it basically also reduces in terms of cost. The cost of GaN on silicon is comparable these days to silicon rad-hard MOSFETs. And while getting all the merits of it, you get the total mission cost also can come down. I've talked about all of benefits of these. Of course, there are challenges. As an engineer, we have to always be worried about what is the challenges. So in the first and foremost challenge with GaN is actually the GaN gate is super sensitive. Some of the traditional customers are reluctant to actually adopt it because the gate and the reliability of the gate is super critical for our satellite kind of space use cases. We at Infineon IR Hi-Rel have a huge GaN portfolio. We not only have the GaN power FET, but also have the GaN drivers that go hand in hand to make sure that the reliability care abouts are addressed. We also have some power stages where the GaN and the GaN driver could be in the same package. Overall, I do expect GaN to get adopted widely, and we are very aggressively pushing the portfolio for both traditional geospace as well as LEO space with a rad hard and rad tolerant products.
Well, you certainly pointed out a lot of advantages to the GaN technology, so you can see why it's being more widely adopted these days. So thanks, GP, for talking with me today about the Infineon Hi-Rel gallium nitride technology. It was very informative. To our audience, you can find more videos at videos.microwavejournal.com. Thanks for watching.